Got it. Thank you. So normal distribution, the mean and the median are both right in the middle. Okay, so is the mode, by the way. This is, some people get weirded out by this, like this is a picture, if you will, of what the histogram would look like, okay, if you're graphing a histogram. Okay. Lots of things in our daily life look like this: IQs, heights, weights, and so forth and so on and so forth. Okay, and so you may have seen this in the past. Someone may have shown you this. I like to draw this a little bit better. Normally, when I'm just drawing sketches, I think that's what I draw. There it is. Boom. It, to me, helps me to sell the bit. However, I always like to make sure that I pay attention to this. Okay, and it's really hard to draw this for me, so I really have to shut up and just draw it. So. Oh, that's terrible, you jackass. No, that's awful. It's not terrible, but it's not good. Okay, so the reason I like to take the time to draw that is because right in here somewhere, you can see it. There is what we would refer to as a point of inflection, yes? Point of inflection. And that happens, of course, on both sides, where it changes from being concave up to being concave down. It happens again over here as well. Okay? And that always happens on a normal distribution, one standard deviation from the mean. And if you draw this correctly, then it really helps you to visualize what's going on here. So in here, wow, what percent is between here, that is -1 standard deviation, and +1 standard deviation? Well, it turns out it's about 68% of the data. Okay. Now, when you just draw one like I did on the previous page, and there's, you know, wee, like that, you don't see it as well. I can draw this and stick it in here and be like, well, that doesn't really look like 68%, Jay. That's right. It doesn't look like 68%, because if you don't draw it such that the points of inflection occur, like, you know, where they're supposed to, right in here, that the visual isn't quite as good. Now, again, I don't care for just a quick sketch. To me, the quick sketches, I think, just help me to visualize what's going on. But that is the real true deal. If you go out another standard deviation, that is 2 standard deviations and -2 standard deviations, okay, between here and here, that is, well, that's most of it, Jay. That's right. It's 95% roughly of the population are within 2 standard deviations of the average. Well, wait, well, what about 3 standard deviations? Yeah, what about it, sir, ma'am? Well, 3 would be out here somewhere. Wow, how much is, well, that's not even close. It's out here somewhere, you ding dong. Somewhere out there. That's -3 standard deviations, and this is, you know, +3 standard deviations. Well, between here and here is how much? Well, it's obviously more than 95%, and it turns out it's about 99.7%. Okay, and this what's called the empirical rule sometimes is approximate values. We are not going to quote unquote approximate them, but we will actually get the exact figures for that. Okay. This normal distribution, if you watch the video, has a PDF. There's some constants out front. I'm not going to really worry about that right now. But the gist of it, it's this thing right here. There's some extra stuff sometimes, but that's the gist of it. This thing does not have an integral in closed form. You cannot integrate it and get, you know, 2x plus 5. Okay, it doesn't work that way. And so as a result, to get this problem, you're going to have to do numerical integration. And so Excel, computers, calculators, everything has a built-in program that says, hey, listen, between here, wherever that is, and here, wherever that is, how much area is under the curve? Of course, that'll be our probability. And you'll type in a lower bound and an upper bound, let's say. And then what will it do? Obviously, it'll just find it. It'll find the numeric integration under that curve. Okay. And so all these routines, all these algorithms have been programmed in. But the cool thing is, for people that have had calculus, it makes so much more sense why things work the way they do. Like, I remember when I first took a stats class, they gave us a table in the back of the book, and it says, use this table. Well, all it is a table of people who printed off, you know, the answers to a bunch of calculus problems. But it always went from clear on the far left at -infinity, way over there somewhere, and it integrated over to, you know, to wherever it stopped. Well, why would it do that? Well, because that's how we integrate. We integrate from the left over to a certain value. And since we don't know where we're going to start always, like say go from A to B, what we always had to do back in the old days, because I'm old, is you'd look up from negative infinity over to A, and it would tell you however much. Let's say that was 7%. I just pulled that out of my butt. Don't ask where that came from. And then what about from negative infinity all the way to B? Well, that was 52%. Cool. So then how much is between the two of them? I don't know, 45% or something. That's how we would do it back in the day. But we, the kids in that class, we hadn't had any calculus at that point, and it didn't make any sense to us. The guy could have told us that. I've been like, I'm sorry, integrals are what now? And so I think that's what kind of neat about that. Also, that is how Excel still does it. You will put in an upper bound. It will integrate from negative infinity over to the upper bound, okay? The calculators have taken it a step farther, and they've given you an A and a B because, that they were designed to do integrals, and so they understand that. Again, we'll run through some more of this bit later on. Again, I don't think that it's necessary that you draw it out, but except for maybe the first time when you first look at that, you're just like, oh, now I can see why it looks like 68% and why, geez, that really looks like 95%, okay? Something that I always like to talk about is people's heights. To me, it's just so easy to visualize heights, and I just don't care. I mean, people are what they are, and I happen to be medium-ish tall. I find myself looking at myself as medium-ish tall. For those who never see me in person, except for this mugshot, I'm 6'3", but I don't really feel like I'm that tall. My kids are 6'6" and 6'4". I got a lot of people in my life that are as tall or taller than me. I feel pretty average height-ish, okay? Now, some people want to get around and I'm like, wow, okay, I guess I'm taller than I thought I was, okay? It really is relative, and it's something that we notice in our daily lives. When I played football in high school, I was one of the bigger kids. We played on a team that was a big team. When I went to college to play, I went from being on a team that we shoved the ball down people's throats because we were bigger than them to a very finesse team because we were very small. And it all depends on who you're comparing yourself to. And that's the normal distribution is all of it's about. It's always, we're going to compare an individual or maybe a sample from that group to, what we're talking about there. So in the case of heights of men in the US, it's roughly, the average is roughly 5'10", give or take, okay? And the standard deviation is about 2 inches, give or take. So 72, 74, 76 inches, okay? Just counting off by standard deviations, 68 inches, 66 inches, 62 inches, okay? Now, if someone asked you, hey, what's the probability I see someone today who is exactly 65 inches tall, you would say it's 0, okay? And why is that? Because you'd be integrating this PDF, we'll call it DX, from 65 to 65, which is a big fat goose egg, okay? So that obviously, can't happen. However, what you could ask is, what's the probability that some random person that you select, I'm just going to pull a name out of a hat, it's a man's name out of a hat, I'm going to pull a name out and I'm going to look at it, what's the probability that his height is bigger than or equal to 65 inches? And the answer to that, well, I don't know. Well, let's find out. Now, it's at this time that we're going to talk about not this distribution, but we're going to talk about the normal, or the standard, almost screwed it up, the standard normal distribution, okay? Now, the standard normal is very similar to this guy up here, except, well, that's a terrible drawing. That's still terrible. And this is why I don't teach art, in case you wondered. All right, cool. The idea here is that 0 is going to be in the middle, and we're going to count off by the number of standard deviations. Okay, so in an instance, for 65 here, well, what is he? Well, I don't know. It's 5 inches below the mean. 5 inches below the mean. How did I get there? Well, I went 65 minus 70. That's cool. It's -5. But how many standard deviations is that? Well, I don't know. You have to divide by the width of the standard deviation. Oh, it's -2.5. A person who is a boy, a male, because we're talking about males' heights here, a male who is 65 inches tall, is 2.5 standard deviations below the mean. And this thing you just did right here is what is referred to as creating a z-score. And so a z-score is really just truly how many standard deviations above or below the mean this person's value is. So it's always going to be x minus the mean divided by the standard deviation. And most books will write it like this initially, where mu is the population mean. And this guy, sigma, this is lowercase sigma, is the standard deviation of the population. Okay. Oftentimes I will get in the habit of writing it like so. Oops, x, you jackass, maybe if you do it right. X minus x bar, there you go, divided by Sx. That is, I use the sample average and the sample standard deviation. But from time to time, I'll go, one way versus the other. In practice, we do a lot of this because we don't know this and we don't know this. Okay. But for the purposes of what we're talking about right now, it's not a huge concept. So what we're saying is being here at 65 inches, which is what we're talking about, is the same as being on this guy at -2.5 standard deviations. Now, there's a reason that we do this. Well, there's several reasons. Number one reason is because in the old days, we always had to go back to a book that had tables in it. And it didn't have this distribution in it. It just had the standard normal distribution. Making this z-score is often referred to as quote unquote standardizing the scores. So it gives you a way to compare. Okay. If someone tells you they get a certain grade in my class, but they got a certain grade, different grade, let's say in Hammond's class, then what do you automatically do? Oh, well, and then so in your head you start interpreting it. Well, you scored this, but this one's harder than that guy, and so on and so forth, and whatever. I used to teach with a guy here at the high school, and if you could put up with this crap, and that would be hard to do, I think, as a high school student, because he was just particular about everything. Ooh, I don't like the way you dotted your I or whatever. He's just weird. If you could put up with that crap, he was the easiest teacher on the planet. And he would always come in, hey, Jay, I got that. My average on my last test was an 82. I'm like, good for you, Bob. You have all the compliant children, and you always write a ridiculously easy test. My average was like a 72 or whatever. Like, ooh, and I'm like, yeah, but I got like a couple of knuckleheads that shouldn't be in here that get like 12% on the test, and then a couple other people that got like 105. Like I had to throw them out because they got hundreds, and then like give them some extra credit or whatever on the curve or whatever because everybody else did so crappy, or whatever. And so my standard deviation was huge because I had the haves and the have-nots. He had pretty much this tiny little window in there. Plus, he was easier. So you could score an 84 in his class and be like right at the average. You score an 84 in my class, you might be quite a bit above the average percentage-wise. But we would standardize it and say, listen, I have like a 0.2 z-score in Mr. Craig's class, and I have like a 1.7 z-score that with the same 84% in Jay's class, I'd be way higher than the average in that class. Okay, again, it's all about giving us a way to compare. How does this person, I like to put myself into it, how do I compare in this group of people versus how do I compare in this group of people? Okay. The story of my life has always been things like, you're pretty good, comma, and then they hit me with the backhanded compliment when I was trying to get into college football. This one coach said, hey, you got really good SAT scores. And there's this long pause. I hear him putting a comma for a football player. And I'm like, ouch. And then, like, hey, you're pretty fast, comma, for an offensive lineman. And you're pretty good for and you're like, oh, dude, that sucks. Well, what's that saying? He's like, yeah, I'm a fast guy compared to all the rest of the hog body offensive linemen. But then what would always happen is like, well, you're too fast around those guys. Go run with these linebackers. And all of a sudden I'm one of the slowest guys. And it's kind of sad and irritating. So it's always about the z-score. The standardized situation is, how do you compare in this group versus how do you compare in this group? That's the whole point of this. So it gives us a way to compare. We're 2.5 standard deviations below the average here. Now, the reason we did this again is, okay, we're going to use Excel. I'm going to quit sharing this and open up Excel for me. Maybe. I'm going to share this with you in a jiffy. So we're going to use Excel to compute these values first. Now, If you want me to, I can use it in the calculator as well, if that would make you happy. But I think I'll go Excel first. Excel is kind of my go-to on this. So what I'm going to do is going to go equals norm dot s dot dist. Oops, I don't know how to spell. There you go. And so it wants a z-score. Well, my z-score was negative 2.5 here. Okay. And then it says cumulative. Well, it's always cumulative. And I literally mean always cumulative on a normal on a continuous distribution, in this case a normal. It has to be, because the probability you get exactly 2.5, big fat goose egg. Not really sure why they programmed that in, other than I think, you know, computer programmers cut and paste, you know, paste in a different PDF. Oh, we forgot to quit asking about cumulative. I don't know why they do it, but there it is. And so it's 0.00621. That's a percentage. That's a probability. Well, what probability? Okay. Well, that means that from here down is 0.00, what did I say? 621. 621. Now that's not what I asked about. I wanted to know from greater than that. So obviously I'm gonna do 1 minus that, because obviously there's 100%. So I will do that on a calculator here and get back to you. 1.
I think you're missing a 0.
Did I forget one? Oh, you just a minute. I don't subtract too good apparently. 1. Well, oh, for God's sake, just a second. 0.00621. Wasn't it just 2 zeros?
Yeah, I got
right.
0.99379.
Yep. That's what I got. 0.99379. Beautiful. 0.99379. In other words, what is the probability you will find someone who is a full-grown adult human in the U.S. who is taller than 65 inches? It's like 99 point whatever %. Okay, pretty easy to do, kind of fun. That's kind of neat. What if we do the same thing, but let's say what's the probability that someone is between, again, this full-grown individual here, between 68.5 inches tall and, oh, I don't know, 71 inches tall. Okay, I don't know. Again, I'm just going to draw the picture. Here's 70, 72. Doesn't take a rocket surgeon to see that 71 corresponds to a z-score of 0.5. Now, I did that in my head, but again, it would be 71 minus 70 divided by 2. Positive because it's above the average. Okay. This guy here obviously is going to be negative, so 68.5 minus 70 divided by 2. So is that negative 1.5 divided by 2, negative 3/4, I guess. Okay. Now those are the z-scores. So again, what we're actually computing is this guy. Here's 0, 1, 2, 3, -1, -2, -3. And we're computing from about here to about here is what we're looking for. Okay. Now in Excel, let me share that with you. Give it to me. So in Excel, it's going to look like this, equals norm. Now I'll do it in 2 pieces. Oops, norm dot s dot dist. I'll do it 2 ways. I'll do the 0.5, I guess, first. All right, so from there, from 0.5 on down is 69%, and then equals norm dot s dot dist, and negative 3/4. You get 22%. So the difference between them is the amount that lies between them. Okay, so it's about a 46% chance, or in other words, another way of saying it would be 46% of the population of adult American men are somewhere between, what did I say, 71 inches tall and 68.5 inches tall. Okay, remember, probability, proportion, percentage, potato, vodka. All right, depending on the situation, I may refer to it as a probability. Depending on the situation, I might talk about it as a percentage. Other times I feel like a proportion maybe captures what it conveys when I'm trying to put out there more. It really doesn't matter. because they're all the same thing, okay? Rarely do I go, I'm going to reach in and pull a name out of a hat. It's not something I'm going to say. So I don't normally say, what's the probability I find someone that's between here and here? Rather, I would say something like, what proportion of American men are between this height, or what percent of them might be, because that's just what I'm asking about this time. Rarely do I find myself reaching in and drawing names out of a hat. What's probably that they weigh this much or whatever it is. It's not something I do frequently. Okay. Yeah. Again, the idea here would have been you'd be integrating that PDF, which again is, I'm not going to bother writing it down. It's not important. And I'd be going from 68.5 to 71. And remember, that is exactly the same thing as going from negative infinity to 71 minus negative infinity to 68.5. That's why we learned that back in Calc 2, okay? So this is the one norm S disk, this is the other norm S disk, and then subtract the two, okay? On the calculator, let's do 89s first. Does anybody have, the 89 works pretty much like the Inspire. So if you've seen it on this deal, the only difference is knowing where to find it. So on the 89, if you're going to use 89, which is totally fine by me, it's under stats list editor, or not stats list editor, you dummy. Hang on. It's under, yeah, stats list editor. I was right. Good for me. Ha. So apps, stats list editor, boom. There's a chat. You shared the screen itself, not the application. If I share the screen, what? I can share just the screen? But oh no, I clicked the wrong button now. Where's the damn button? No, I don't want that. I can share just this. How do I? Oh, I have to stop sharing first. How do I share? Oh, just share screen. That's all I do. Oh, that's what I did. Oh, computer sound optimize. What am I doing wrong? Advanced? No, I don't know what to do. Oh, I just clicked just screen. Duh. Thank you. Nice work, man. Nicely done. Beautiful. All right, there it is. So then F5, and then if you go down here to normal CDF, and so in this case, and you can do it the way, you can actually do it without converting it, but I just leave my zeros and ones down here in the bottom. You see that? That leaves me in a standard normal situation. But what I would do instead is I'd put in my negative 0.75, and I'd put in my positive 0.5 right here. And I would get 46%, just like you thought I should. Okay. I don't know if anybody has the 84. I'll just run out. Let's put one of those up here real quick. The 83, 84, same calculator. It's here too. It's under distribution, right on top of the little bars key right here. If you go second distribution, normal CDF. And this one doesn't allow you to do an upper and lower bound, so you would put in 0.5. Oops, I lied to you. Just a minute. Maybe I lied. Maybe it does give you one. Maybe it does. It's been a while since I played this one. Negative 0.75, comma 0.5. Oh, there it is. Yeah, I guess it does do an upper and lower bound. If you don't specify, it assumes you mean standard normal, because again, that is the standard that we all use. We always use a z-score when we talk about standard normal. Again, standardizes everything, makes everything look the same. Okay. Again, I'm going to try to draw that picture Bob Craig and I had back in the day, where he might have had an average for his class might have been an 80%. And his standard deviation, it might have been something like 4. So 84, 88, 92. I mean, he didn't have any really good kids in his class, obviously. They weren't like high flyers or anything. But he didn't really have a lot of, lows either. Versus my class might look something like this. And my average might have been a 73 or something. I don't know. I just made that up. And my standard deviation could have been, I don't know, 20. No, that's probably too much. No, that's probably about right. 20, sure. No, that's a little too much. Let's don't get carried away. Let's do 15. Let's do 12. 85, 97, 109. Probably nobody scored that high, but whatever. 61, 49, what, 37, I guess, right? Cool, whatever. If you scored a 70, no, let's do an 80, say you did an 84% in Bob's class. You are 1 standard deviation above the mean in his class, okay? In my class, you're actually less than 1 standard deviation above the mean. Why is that? Well, because I have a huge standard deviation. I have a huge standard deviation because I have a lot of variability in my class. We weren't all just tightly packed, very homogeneous, more heterogeneous in my classes. Everything's spread out all over the map. Yeah, and I never forget this one class I had in high school. I had 2 classes 1 year of stats, and they were the weirdest classes ever. One class was the most boringly normal everything. And what I would do in the start of the year, I would get their vital statistics, heights, weights, or not weights, heights, ages, their mom's age. I use that in an experiment later on, a bunch of different things. And it didn't matter. The one class was like boringly just straight down the middle average. There was no tall kids. There was no short kids. Everybody was just average. And it was true of everything we did in that class. Everything they did was just average. The other class was insane. There was 4 or 5 boys taller than me. There was a girl that was as tall as I was. On the other end of the spectrum, there was 2 girls that were sub 5 feet tall, and a boy who was like right at 5 feet tall. And the coolest thing was their average from both of those classes was exactly the same. It was whatever it was, 5'9" or whatever, 5'10", whatever it was. It was exactly the same for both classes, which was just nuts. But the standard deviation for the one class was huge by comparison. And so I don't know if I mentioned that before. It just still blows my mind. That's why you talk about things so long after the fact. It's because the probability of them happening is so small. Now, what I want to talk about now is to lead off from this, once we understand that concept, and get into the concept, what's called the central limit theorem, which is arguably the most important theorem in statistics, certainly at this level, but I would argue at most levels. Okay, the central limit theorem says this. It says regardless of the original distribution of the data, that's the x's, okay, the x's, okay, regardless of what they came from, doesn't matter. Could be binomial, could be exponential, Poisson, hypergeometric, doesn't matter. Could be some weird distribution you never heard of before, doesn't matter. Could be a what we call a uniform distribution where everything is exactly the same probability, doesn't matter. The sample averages will be distributed. Those are the X bars, by the way. X bars will be distributed normally with the same mean. I'll write this out first. Normally. So they will follow a normal distribution with the same mean as the x's, but the standard deviation will be divided by the square root of the sample size. Okay, so in other words, it says this: the x's will have a mean, we'll call it mu. They will have a standard deviation, we'll call that sigma. We know nothing about how they're distributed, and we don't care. Okay, we are going to take a sample from this population, and from that sample we will find our x bar. X bars will have, we say it this way, this means is distributed normally, so we use n for normal. You want to know some fancy things, you write bino if you mean binomial, you write geo if you mean geometric, things like this, but n is the universal for normal. You'll have the same mean that we did over here, but the standard deviation will be divided by the square root of the sample size. Now, there's a couple of things that are kind of weird about this, and a couple of things that make sense about this. This part right here, if you think about it, makes a lot of sense. When someone tells you, hey, go take a sample of how I don't know how tall people are at OIT, and you go out in the Commons and you find the first person you run into, and you say, how tall are you? And they say 5'2", and you're like, sweet. Look, I just took a sample. The average person at OIT is 5'2". All right. Well, how many people did you ask? One. Well, that's ludicrous. That's ludicrous. Well, okay. Oh, so I should ask two? Sure. Yeah. So they go back out, they get a 5'2", and then they ask somebody else that's 6'7". All right. I can't do that in my head. 2 plus 79. 1, carry the 1, 141 divided by 2 is 70.5. Awesome. The average height of people at OIT is 70.5. Like, well, how many people would you ask? Well, 2. Well, that seems pretty variable because we were all over the map. We're over here and we're way over there. We could be all over the map in this situation. However, what if you took a sample of size, I don't know, let's say, what if you asked a sample of 1,000 or 100 students at OIT, okay? Well, what is that going to do? The average, it doesn't matter which 100 people you randomly ask. It doesn't matter because in each sample size of 100, you're going to get a couple people that are 6'6", and you're going to get a couple of 5-footers. And guess what they're going to do? They're going to wash out. And where's the average going to land? Right where it's supposed to. What do you mean right where it's supposed to? Well, right where it is, right where it should be for the population of whatever you're looking for. Whether let's just say it's men this time. Okay, it's going to tend to coalesce right there at what the unknown average is, because we don't know what the true average is. We have a pretty good idea. How did we get that idea? We asked a lot of people, how tall are you? And then there it is. The similar thing will be true later on. You might want to know the average wingspan of one of those murder bees or whatever that are flying around now, apparently, or whatever. Well, you go catch you a bunch of those suckers. I don't know what the average is. Only God does, and he's the only one that cares. But I would like to know an idea. So I catch 100 of the little beggars, and I stretch them out and 2.5 centimeters. All right. And then I measure a whole bunch of them. And over time, all the freaks will tend to wash out, and they'll tend to coalesce at what the average is. Okay? Now, what that's saying to us is this. You take a whole bunch of averages, like a whole bunch of different samples of size 100, like a lot of them. And then you look at those and you graph those sample sizes of size 100. What you will see is this. When you graph, and now these are all of the different averages. So I found the sample size of 100. I found a whole bunch of them. And I graphed their averages. It will always come out being normal. And there will be very little variability. Let's say the average height was supposed to be 70 inches. When we're done, we're going to find that the average height is, by God, 70 inches. And what is the standard deviation? Well, I don't know. It's whatever the standard deviation was previously divided by our sample size. Now, to show this to you, I'm going to generate some data randomly. Back in the old days, which were not really the good days, I would make kids do that by hand. We'd roll dice, and we'd roll dice, and we'd roll dice, and that's not cool. That's why the good Lord made Excel for us, okay? So we are going to pop open some Excel here, and I'm going to use the other computers a little faster and a little more fun. I think I am just going to straight up roll some dice. We could do D10s or D20s or something, but it's too much work. So I'm going to stick to just a regular 6-sided dice, if that's okay with you. And of course, I can get 1s and 2s and 3s and 4s and 5s and 6s. Nice. And of course, their probabilities, I'm going to write right here, 1 divided by 6, because I can. I'm just going to copy that down. Now, you cannot, just a word of warning, you're like, I'm going to play along with this. This is just demonstrating how the central limit theorem works. So you're not going to really do this in a class. Once you get central limit theorem and how important it is and how cool it is, and which is really neat, by the way, to do that. But once you get that, it really, I think, helps you when you do other problems, but you're not going to do what I'm doing here to do that. So what I'm going to do is I'm going to generate some random data. So I am going to roll these dice. Oh, let's see. I want to do this 1,000 times. And I'm going to do generate 1,000 random numbers each. So I'm going to have 1,000 columns, 1,000. Actually, I'm going to do 100 columns. 100 columns, and there's going to be. I'm going to roll a dice in each column. I'm going to roll it 1,000 times. Okay. So in a minute, I'm going to go from A to, I think it's going to be CW is 100. Okay. And in each column, there's going to be 1,000 rolls. So 1, 2, 3, 4, 5, and 6s, and so forth. Okay. Now, when we do this, there we go. New worksheet will be fine. Betsy does not like having to generate this much data. She really doesn't like it when you make her do 1,000,000 data points. Boom, there they are. Okay. And by the way, I didn't have to listen to dice clanking on the tables all day. Okay, there we go. Now, what I can do is come to the bottom of this guy, and I can go, let's find the average equals average of this column. So that's A1 colon A1000. Nice. The average roll in that column is 3.4. Oh, by the way, what should it be? Equals, remember, expected value is X times P of X, yes? And then take the sum of those guys. Oopsie daisy. So the expected value should be 3.5. Oh, mercy, look at where we are. We're just a little below 3.5. Well, let's see what happens when we go this way. Come on, Betsy, you got this. There you go. Oh, it's CV, I'm sorry. Hey, look, they're all right around 3.5. What do you know about that? Check this out. What if I did this? What if I did this? What if I said, let's find the average. Average. Oh, we can't spell, no. Let's find the average of all those guys, shall we? Well, now, no way. 3.495. That's about as close to 3.5 as you will ever get. Now, I wonder what the standard deviation is. Standard deviation. If you could spell, it would be helpful, dummy. The standard deviation is for this column. Let's find out. So A1 colon A1000. Boom. And it's 1.7-ish. Now you're like, well, freaking birds are kind of loud tonight. Equals, remember, we need the second moment. So that's the X squared times P of X's. Excuse me. And I'm going to find the sum of that. And then I'm going to take equals, remember, it's the second moment minus the square of the first. And the standard deviation should be 2.9. Well, wait a minute now. Yeah, what's going on here? That's kind of weird. Oh, wait, remember, you got to square root this guy. So you're like equals square root, remember, because that's the variance is what you just found there, right? So the square root of this guy is 1.7. 1.7. Hey, that's exciting. Now, what I'd like you to see is this, though. What if I found the standard deviation equals STD, the standard deviation of all this data that I just found? In other words, if I go from A1002 colon CV 1002. Whoa, look at the standard deviation. It got tiny on me. It's 0.05. Now, I don't know if I recognize that guy. Actually, I do. 1.7 divided by the square root of 1,000, because that's my sample size. There's 1,000 in each of these columns. What do you know about that? It's really close. It's 0.053. Now, again, remember, I cannot take every sample size of 1,000 that there is. I took 100 of them. Okay. Now, had I taken more of them, would have been better. Okay. Now, the cool thing about this is, well, it's twofold. First of all, if you come across here, you will notice that none of these numbers are bigger than 3, and none of them are less than 3. And in fact, maybe this 3. I thought I saw a 3.8, but I don't see it. They're all right around 3.5. There's very little variation. There's very little standard deviation. That is why when you do this, and you take these large sample sizes, the standard deviation was always going to shrink because there's very little variability when you take a decent sized sample. Take a small sample, there's variability all over the place. We take a huge enough sample, like, oh, yawn, yawn. That's exactly what we expected to happen. Okay? Now, I'm going to show you one more cool thing just for visual purposes. I'm going to do this a couple different ways here. I'm going to show a couple things. So let's copy, Control C, start a new page over here. I think I can do this if I'm careful. Paste, transpose. Damn it. Oh, I hate when I do that. All right, back up. I got to do this first. I forgot. You have to paste values only first. There you go. Now you Control C it. There you go. Now you can transpose. Bam. Now, while I'm at it, I'm also going to select one of these columns, and it doesn't really make any difference which column I select. Okay, what I want to just show you is these are both Control C. Averages, I don't know, X's, whatever, not important. I'm going to make a pivot table out of this. Oh, what just happened? What? Uh-oh, what happened? What happened? Where did my averages go? Ah, God dang it, I can't even, I'm not even smart enough to do the averages correctly. That's sad. Let's try that again. Let's copy all of these this time. No, they're all there. What the heck? They're all here. That's so weird. Someone's going to tell me how to do it right, I bet. That's cool. Control C. Let's try this again. Let's put it here. Let's do, there they are. Did it go this time? No, what am I doing wrong? Who's unmuting themselves? There it is. Where's the chat? Columns versus rows. You have less columns than rows. Oh, yeah. Duh. Thank you. No, I'm just stupid. So it's not that I can't run Excel. I'm just stupid. There you go. Cool. So I'm going to do this. I'm just going to highlight the first 100. That's not the biggest deal. What I wanted to see was this. Good point. Good point. So I'm just going to highlight these first 100. There you go. Nice work. And I'm going to put them in a pivot table. Again, this is just for visualization purposes. I think it helps to sell the bit. If I do this and this, I can come in here. Oops, I don't want that to be sum. I want that to be counts. And what I'm going to do is I'm going to build a histogram out of this thing. So I'm going to group these guys. Okay, notice I'm going from 3.3 to 3.6. So let's count by like 0.06 maybe, I think. Nice. And so that gives me like 5 bars, if you will. Control C. What I can do then is, I'm just going to paste this over. Just give a quick graph is all I want to do. Just a quick graph, paste. There you go. Insert column chart. Boom. There you go. And what you see here is your histogram. And what does that look like? Looks pretty dadgum normal. Could I make it more normal? I could have made it more normal had I added some more bars. I could have made it a lot more normal looking. Okay. That's a product of me not wanting to do as many bars as I maybe could have. Over here, if you get rid of those and do the X's instead, clearly they go from 1 to 6. I mean, duh. The first thing that comes to my mind is, geez, they're almost identical. And I'll just do it right here. Back with it. Insert chart here. If you were to graph them, this is your histogram. What does it look like? Well, it's supposed to be what we call uniform. That is, they're supposed to all be the same height. They're not quite, but they're pretty close to the same height. And yet we took an average out of them, and what we got was the normal distribution. That is what the central limit theorem gives us. And it is a beautiful thing, because oftentimes in our daily life, well, in our workaday worlds, if we're dealing with data, we don't always get normal data. We don't always get normal data. So what we can do is we can take a sample from it, and we don't care what it came from. what we care about is, let's take a sample here. That's cool. We can make it look normal. And then here's the best part, because I'm gonna go back to the other computer here for a second, because we're gonna ask and answer the same questions we did before. Okay, we're gonna ask and answer the same questions we did before, but we're gonna do it for a sample, or for a sample size. And so it's gonna be something like this. So previously we said that we know that the average height of men in America is 70 and the standard deviation is 2. Okay, that's great, lovely. And so from this situation here, I'm going to ask this. I'm going to take a sample of size n equals 100. Nice. And what I want to know is what's the probability that x bar, not one of the x's, but the sample average, what's the probability that it is bigger than or equal to 71 inches? Okay. Well, now initially recall that that was here. So here's 70, here's 72. Well, 71 is right here. And although it's not 50%, it's a good bit of the graph. But remember, the central limit theorem says that x bar, so back to this train up a little bit. I'm going to change these to the population so I don't confuse everybody, okay? I'm just going to change those to the population. So recall that the x's are, in this case, we know they have a normal distribution because it's height, and they have a mean of 70 and a standard deviation of 2. But the x bars are normal. They will also have a mean of 70, but their standard deviation will be 2 divided by the square root of 100, which is 0.2. Meaning that now if I make a it's a vector, yay. And now if I make a z-score, watch carefully, it changes a little bit. So instead of being, this is for one person, I'll say one person, it would be x minus mu over sigma. But for a sample, it becomes this, x bar minus mu over sigma over the square root of n. Because this, down here on the bottom, is my new standard deviation. So if I do this, I'm going to get 71 minus 70 over 0.2. And, that's 5. Okay. 5 standard deviations. That's right. So think about this for a minute. Okay. Here's 0, 1, 2, 3, 4, 5. Yeah, how many is from here out? 0. Now, the computer will actually tell you, but it's 0. All right. Right around 2 is where the welcome to Freakville sign is located. And again, right around -2 is right around where the freaks begin. And by freakish I just mean you stand out, okay? There's very little chance of someone being bigger or smaller than that, okay? So if you're over here at 5, say, there's not much over there. And again, how would I figure that out? I would take my computer here and I would say equals norm.s.dist. That's the wrong one, jackwagon. .dist. And I'm going to put in, what did I say, 5, 1. And of course, Betsy's going to say it's 100%, which it is 100%, but it's 100% from there down to -infinity. So I'm going to put 1 minus. And so there it is. She's not going to lie to me and say it's 0, but for all intents and purposes, it's 0. There is no way that the average is going to be 5 standard deviations bigger, okay, than the average. There's no way that's ever going to happen, okay? Now, so let's see where to go, back to here. Okay, so that's fine. That's lovely and everything. Where does that come in engineering? And this is the key why we study these things. Because you know as well as I do that anytime you run in a manufacturing plant, or basically anytime you're doing anything in life, you need to know, is everything okay? Or the converse of that, or is anything going wrong? Is something wrong? Now, let's just pretend that we have some machine here. It's just cranking out, I don't know, widgets. There you go, whatever. And they're supposed to have, because we are manufacturing, I like to do like washers. They're easy to visualize. Like this inner diameter is supposed to be a 1/2 inch. How much slop should there be in my washer? Well, it's a washer, so it's not like it's the most precision manufactured thing. But let's just say that it's 0.5 inches in diameter, and the standard deviation is something like 0.012 inches or something. Okay, lovely. That's what it's supposed to be. And so the reason that we study these things, like, for instance, the central limit theorem, is this. I'm going to take a sample every hour, let's say, or every hour or twice a day, or whenever you're going to do it. And what I'm going to do is I am going to compute X bar. Cool. And so I'm going to find the sample average. Now, if it was one, so let's do this first. Let's say this. We are going to shut the machine down, shut it down, if you get one washer bigger than 0.525, sure, or smaller than, I can't subtract, 0.475, I guess, right? Yeah. Now think about what that would do for you, okay? Again, this is just totally hypothetical here. So here it is, 0.5. We're going to count off by 0.02, so that's 0.52, 0.54, that's as far as I needed to go, I guess. And then 0.48, 0.46, and again, that's as far as I needed to go. So we're talking about right here somewhere. I'm talking about right here somewhere, okay? But I'm talking about not the area between them. I'm talking about this area out here and this area out here. So in other words, every one of them that's coming out is in essence as if the good Lord himself is reaching into a pot and dragging them out one at a time. And you can visualize it like that. So I reach in, I pull one out, well, not me, and it pulls it out, and then there it is. What's the probability that it either lands over here or over here? I don't know, let's find out. So equals norm, come on, Jay, equals norm dot s dot dist, okay? And I'm going to put in initially 0.4, okay, everyone saw what I did there, didn't they? I blew it. I didn't finish the problem. So what I'm going to do on this is I'm going to first of all make z-scores for those guys. So let's do this right. Let's do it right. So I would do z equals, and again, this is for one washer, it's going to be 0.475 minus 0.5 over 0.2. Can't do math in my head. Whatever that is, so 0.475 minus 0.5 divided by 0.2 is, what did I do wrong? Oh, it's 0.02, you dim bulb. Negative 0.025 divided by 0.02. There you go, that's more better. Negative 1 1/4, which makes sense. This is so we're talking about 0 here, negative 1 1/4 z-score here, and this one over here is the same, 1.25. And now the nice thing about Excel, or I mean the nice thing about the normal distribution is there's no thinking involved. It's perfectly symmetric, just like how I like to go this, like my art symmetric too. I don't like a weird arm on one side, not on the other ones, okay? Norm S dist, and I'm going to put in negative 1.25, comma 1. And so you see it's about 10.5% from here down, so 0.105 from here down. Well, because it's symmetric, it's also 0.0105 from here on up. In other words, there's about a 21% chance I shut the machine down well, pretty much every time I grab a washer. Now that is not acceptable. That is unacceptable. I don't want to be shutting my machine down this often. And so what I do is I don't take one washer. That's ludicrous. I take a sample. So let's take a sample of 100 washers, or whatever you like, 64 if it makes you happy. I like to use squared numbers, but you do you. And if that were true, then look what's going to happen. Then that means the X bar will be distributed normally. It'll still have an average of 0.5, that's true, but now it'll have 0.02 divided by the square root of 100, which is 0.5 and 0.002. Nice. Now think about this. Think about this. That's going to be what I just did up here, so negative 0.025 divided by 0.002. Dude, that's 12 and a half deviations. Wait, 12 and a half? Yeah, 12 and a half, man. So like, here's 3. There's nobody from here up. And you're over here at, 12 and a half. In other words, it would take a lot to be wrong for you to really have a problem here. In fact, just for fun, if you were to count this out, here's 0.5 here. This is 3 deviations. This would be 1 deviation would be 0.5002. 2 deviations would be 0.5004. 3 deviations would be 0.5006. Now think about this. How far off would you have to be to reject? Well, now remember, I just told you the magic number is roughly 2 standard deviations, right? And so you would be really close to the magic number of 0.5, and you'd still be shutting things down. Why is that important? I don't want to waste a ton of washers going out the door, or a ton of raw material, or more importantly, have people coming at me on Yelp going, oh my God, he makes the worst washers or whatever. I can't deal with that in my life. So what I want is I want to be able to catch things quickly. And so what I do that is I take a sample, because the sample is so less variable compared to the actual values. And therefore, I can actually catch problems because it doesn't, the X bar doesn't have to be very big at all. Again, we would typically come in right around here. Again, 2 deviations, that would be very weird for us. Somewhere around there, we would then go, whoa, shut the machines down. We've got a problem. And you're like, but they look great, boss. Yeah, I know, but I took a sample size 100 and I got 0.5005. Oh, shut it down. And the cool thing is, from a manufacturing standpoint, you can keep a very tight tolerances on these things. Now, something else we're not going to get to do in this class because there's just no time in this class for it. It's not what this class is about, which I find a little unfortunate, is reality when it comes to manufacturing. It's not the average. You cannot sell this ginormous washer like this and then a couple of these little fellers and whatever. And you're like, well, by God, the average is a ½ inch. No. Well, it is. But it can't have that much slop. And so more important, sometimes, a lot of times, more important is not so much the average, but the standard deviation. I cannot have variation. I cannot have giant swings in variation. When people buy my product, they buy my product expecting the same thing every time. And I cannot have them having these wild swings, okay? And so it's unfortunate that doesn't get covered in this class. I always think back to a friend of mine. He makes kombucha, and he's actually, as far as that crap goes, he's pretty good. But when he first started making it, it was not good. It was not. And it was like, okay, this bottle isn't bad. Oh, this is terrible. Very Saturday market feel to it. Like, it's artisanal or something, so let's charge more. I don't know. But to the point now where his stuff, when he makes this batch, by God, it tastes like this batch every time. Okay. Companies like Budweiser have this down to a science. McDonald's, things like this, where it's just bing, 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 bing. Well, people always laughing when I say Budweiser, but okay, they make gazillions of bottles of beer a year. Okay, they know what they're doing. Oh, it tastes like swill. It tastes exactly the same every time, sir, ma'am. There's no variation in the stuff. Okay, it doesn't matter if you like it or not. The point is they have that baby knocked down tight. And again, that's where we're going to see a lot of in you guys are going to see a lot of it's always so. There you go. The idea is that when you do statistics, it's all about when you got stuff coming off a manufacturing line, I have to have a way to check quality assurance. And so one way that you'll do it always is with this central limit theorem. You'll take a sample size of n equals whatever, and you will create a z-score for it. And then typically, will have some cutoff range. Like, in other words, I would like it to be such that, you know, there's somewhere over here where I have very little chance of being wrong. And typically what we do is we like to put 95% in the middle. That's a pretty typical conclusion. That would mean we have about 2.5% down here and about 2.5% up here. And where that happens, there we actually have a button for that on a calculator or in Excel, either one. That's kind of a cute ghost picture, isn't it? You go away, I don't want you anymore. There you go. So, and the way to do that would be equals norm S inverse. And I'm going to put in 0.025. You always put in area to the left. So what that's saying is that from here down is 2.5%. It's about 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So again, like I told you, right around 2. And that's typically what we do. We typically stick with 95% in the middle and 2.5% total on the outside. That's usually a pretty good way of doing it. It gives you a pretty good target and being able to sell something. Like if you're telling someone you're a good shot, I'm such a good shot. I'm saying, okay, what can you hit? Well, look, if you can hit a plate at 100 yards, let's say, okay, you're a decent shot. Okay, you're a pretty good shot, whatever. Now I get the side of that gymnasium. I'm like, okay, from how far away? Well, I think 100, 10 feet away from it. You're not much of a shot, sir. That's not saying anything, okay? So I need a small enough target to impress people, if you will. But I also have to be big enough that I can say I did something with it, okay? So I don't want to have this like make this ginormous target that I can never miss, all right? So this is kind of the best of both worlds. It's typically this 95%. That is for the quote unquote hard sciences. For the more softer sciences like psychology and stuff, they typically use 90%. And that gives you 90% in the middle. And that equates to about 1.6 deviations above and below the mean. And again, that's just something that we're not going to talk about that much more in this class, but that's typically where it happens. And so if you're running a business, what I would say if I were you, because you'd probably hire some flunky to do some of this stuff, is you'd have a cutoff that says, listen, if the average, if X bar comes out to be bigger than this value, or X bar is less than a particular value, oops, that's the way around, dummy, less than another particular value, hey, come talk to me at that point, all right? I don't really want you doing statistics every time, maybe necessarily, so I give them a cut score, and I say, listen, here it is, here we go. Back to this one over here, just real quick, and I think we'll call it a night at that point. Back to this one over here, real quick. In that situation, instead of going out quite 2 standard deviations, I would do 0.002 times 1.96. Give it to me. Plus 5, or darn it, plus 0.5, you goober. So 0.50392. And 0.5 minus 0.00392. Oh, darn it. 2. There you go. 0.49608. 0.49608. Come talk to me if we get an X bar that lands down there or an X bar that lands up here. That's when I want you to shut me down. Okay. And so that's typically how these things get done. That's just typically how it is in the real world. There's always somebody has made a shortcut for somebody. That's what it's going to be based on. It's just kind of the same process here. Again, central limit theorem is huge. On the test, and you'll see this on the review, I will ask you about, suppose I take one item or one person, and it's going to be some huge percentage, I don't know, 25, 60%, whatever it is. And then I said, oh, wait, I changed my mind. Let's take a sample of, say, 50 people. Oh, my gosh, it's way less percentage-wise or whatever, okay? Big shock, okay? That's just typically how it's going to work out, okay? The whole point of that is, again, a sample is always way less variable than a single individual. An individual can be anywhere. The average from a sample is very constrained. It can't be that weird, okay? Yeah, just think about those sorts of things. So I think last thing when I remember, and this is funny because that story I tell about that one stats class, and there's another story that I tell that I still keep telling them. And I thought about this the other day. This one story is probably 15 years old now. And that means you're like, I'm a grandpa, old guy, something that I tell stupid old stories. But no, this still blows my mind. But the reason it still blows my mind is because of how weird it was. That's the reason it sticks with me. Nobody ever runs home and says, hey, honey, I saw the weirdest thing today. Oh, yeah, what was that? Yeah, there's this girl. She was like 5'5". And that was the end of the story. That's stupid. Right? No one talks about that. You talk about the weird things that you see in the day, the things that are just so improbable of happening. That's what you talk about. So I went into the Fred Meyer and Scappoose one time, again, 15 years ago, probably at 10 o'clock at night. I saw 5 different women that were over 6 feet tall. It was creepy. They were all taller than me. Okay. But if you had just showed up on planet Earth that day and took the average of that sample right there, and you only sampled the first 5 people you ran to, which were those 5 women, right? Think about how skewed your data would be. Because why? Because you took a sample of 5 people. All right. But instead, had you walked around that store, and there are probably 50 or 60 women in that store, and you sampled all of their heights, even though you had those 5 freakishly tall women in that group, you would have ended up with an average that would have been down around where it's normally supposed to be, quote unquote. Okay. It doesn't matter how many outliers on the top end or the bottom end there are. If you take a big enough sample size, like, oh, I saw like 50 women that were over 6 feet tall. I bet you saw 50 women under 5 feet tall too. Yeah, how did you know? That's how it goes, bro. And you sampled like 10,000 women. Yeah. And so you saw a ton of them that were hovering right around 5'5", 5'4", 5'6". Yeah, how did you know? Because that's how it works, okay? And they will average out to where it's supposed to be, okay? So central limit theorem is pretty cool. Pretty neat, easy theorem for you. I throw that in because even though it's mentioned briefly, it kind of gets short shift. I don't like that. That's kind of how it goes. As I say, on the final, I will keep it pretty much exactly like the review that I'm going to send out. Similar questions. The hardest chapter in this book is the one on transformations. Don't sweat it too much. There's one problem on the test like that, and I set it up 100% for you. I give you the transformations. I give you everything. Transformations used to be a big deal back when you guys had a slide rule, okay? Back when you had a slide rule, you'd want to do a bunch of transformations to make your life easier. Algebra was easier when calculus was hard back in the day. Now that I have a computer do my calculus for me, algebra is a lot of work. I don't want to do that. I'd rather just do several calculus problems because it's not me doing the heavy lifting, okay? The computer doing all the hard work for me. So we don't do them as much anymore, although once in a while, somebody might want to know not what X is, not what Y is. They might want to know the difference in X and Y is, and that's probably the only reason we do transformations anymore. But again, it's not something that the average person does very often, so I don't spend a ton of time on them. All right, questions at all? Things you wanted to talk about? Anything else that come to mind that you want to talk about? I just found out the other day that I can do.
Did you say the finals on a Wednesday or a Monday?
Monday, what did I say, the 8th, I think?
Okay.
Yeah, the 8th.
At 6?
6. Let me know if you want to do a different time, Bobby, on your deal there. Excuse me. No questions?
I saw in the
Not
chat.
on a Wednesday again?
Oh, there's a chat. There's a chat. Woo! Oh, you have class on Monday the 8th? Yes, algebra is not fun. How can you guys have another final at that time?
Because we're not scheduled for this until Wednesday.
Oh, I'm sorry. Oh my God. No. Wednesday. Sorry, I forgot what class I was in. Wednesday. Thank you. Wednesday.
I was like,
God.
yeah, the
Sorry,
syllabus
Bobby.
says June
I
11th.
thought that was a weird question, Bobby, but no, just Jay's an idiot. No,
that's okay. Thank you for clarifying.
Oh, yes. Nice. What an idiot. Yeah, so the 20th is recorded, and I'll put it up right after this class. Thank you for pointing me out to whoever said that earlier in the class. And I think the 13th is already up, but I don't know. I can go look at that. I think I recorded them all pretty much because I was told that I was forgetting to do that. So I think we're good now. Yeah, I'll just put up 2 more drop boxes. I'll just have them do I think I'll have everything due on I guess probably have everything due on Tuesday before your final. That just give me a little head start on grade and stuff. So I'll just put those up, Jake. So I'll just put them up sometime. I'll put them up sometime this week, but I'll just have them due on that Tuesday before the final. Cool. All righty. Anything else? Well, have a nice evening. Enjoy the rest of your week.
You too, sir.
I have a question.
Hit me.
All right, so I'm looking at the original syllabus that we got at the beginning of the term. Is that still accurate?
I think so. Unless
All
I
right,
screwed something
because
up.
it says June 11th. Does that sound right? Oh, wait.
Should be June 10th, I
June
think.
10th. Okay, I'll write that in.
Well, hang on. Let me figure out what I'm doing wrong here. Should be June the 10th. It's that Wednesday of finals week, whatever that is. I thought that
Okay.
was that was the 10th.
Yeah, that looks good then.
All right. See everyone. If you're signing off, I'll just double check it real quick here.
Jay, on that note,
Sure.
I had a chance to look at the term project,
Mm-hmm.
and I was let me give you one moment here. I'm gonna switch to my other mic.
Yeah, it should be June 10th. That's weird. Sorry about that, Levi. Yeah.
So I was just looking at some like just 1 and 2 because we have gone over. I think it was E of X, E of Y. Is that correct?
Yep.
So are you giving us like the data in the Excel document that you're giving us? Maybe I should have looked at that.
Hold up here. I'll just pull it up real quick so you can see it here.
I asked about that at the start of class, and he hadn't posted the data. So he's
It's up there
posted
now.
the data.
Yeah.
Oh, okay, okay.
Here, I'll just open it up so you can see it here.
I'm just trying to gauge,
There you go.
you know, like how, I guess how deep the project goes, you know?
So let's just show you here. So back on the OIT page, Canvas. Oh, where is it? Home. Oh, projects right there, dummy. Oh, never mind. Project. Oh, I keep forgetting to hit share. Let's share this thing. Okay, so no, that's the dummy. That's the one you want. Click it. There you go. So looks like this. Okay, and okay, cool. So then what you're going to do is this: you're going to for expected values. Okay, there they are, and then you're going to simulate 2 columns of data. So I will put up a video on how to do that. I think that's the problem with being kind of half. It's kind of screwing me up in terms of my teaching stuff. So I forgot to mention that.
I think I'm kind of,
I'll show you a quick video.
Oh, sorry, go ahead.
So the video is just like we did here on this page here. So this is a discrete distribution. Okay.
Right.
So I'm just going to keep talking. I'll just add this on the end of this video here. So to add this in, you want to go to File, Options, Add-ins, hit OK. Oh, damn it. Just a minute. No, you don't. You go File, try again, dummy. Options, Add-ins, Go. There you go. It's this top one that you want to turn on. And then when you do it, under Data, it'll show up over here. Okay. So Data Analysis, Random Number Generator. And then what I want you guys to do is just do like 1 and whatever I said, I don't know, 100, let's say. Okay, like so. Cool, whatever, there it is. And sure, go. So there's your data, right? And then these would be, let's say, your X's. Okay, that's nice. So you know what the expected value of this is because you know where the data came from. It came from right here. So the expected value is 3.5. However, what I want you to see is this, that this is my X's. And then let's just make up a new one over here where I can do 3, 4, 5. Because I had a dice that was 3-sided. That's pretty cool. 0.3, 0.6, no. 0.6, 0.1. As long as it adds up to 100%, that's totally cool. And then you can go data analysis. I still want 1 and 100. That's cool. But my input range is going to be here now. And I don't want there. I'd like it to be in B2, I guess, for Cool. And so then there is my y's. Now, again, you know what the expected value of y is. You could just this times this plus this times this plus this times this. But what the guy can do is you can actually do x plus y, right? And so it's just equals this guy plus this guy, and then paste it down. And so what you can end up doing is doing the average of that column, which is C2 colon C101, I think. And you see it's 7.36. Well, I didn't do this one, so I'm going to do it right here real quick. Equals this guy times this one. Done. Come on, give it to me. And then equals average of that. It's 1.2. Now you're like, well, that's cool. So where did you get that data from? Well, check it out. If you were 3.5 from before plus this amount, so the expected values should be, did I say that, did I add? What did I just do? Something weird. The average of C2 to CO101. Average. Something screwy. Oh, I know what I did. Here's what happened. No. This can't be right. So what did I do wrong here? So let's see here. So equals that times that. That's true. What's the matter, people? Someone tell me what
I don't think you added them.
Oh, I averaged them. What a goob. What a goob. Thank you.
Not a problem.
There you go. Oh, look at that. 7.3. What? No way. Nice. Now, what if you had subtracted them instead? Oh, that's a good question. I don't know. So what you're going to do is explore this a little bit, obviously. Okay. And if you subtract them here, you will get the same kind of, except this one has to be negative, I think. Oh, no, I did it backwards, you dumbass. Oh, shoot. Anyway, what I want you to do is I want you to explore this. Now, for adding and subtracting, it's going to be very similar for as far as the averages go. But I want you to explore what happens to the standard deviation, and that's the big deal. Okay, and so you're going to find the standard deviation for this guy. You'll find the standard deviation for the other, and then you're going to find the standard deviation of this column here, and you're going to kind of go back and talk about, well, what happens. And so we talked about that back when we first started talking about. We started talking about some of these things. We talked about the expected value of x, x plus y is equal to the expected value of x plus the expected value of y, and that's cool. But then it's not true. It's not true for the standard deviations. So when you add and subtract, you don't add and subtract. You don't add or subtract standard deviations. You always add the variances. Okay, and that's a big deal. Now, again, think about why that would be. So the one I always come to mind is if you had husband's age here, wife's age here, you'd have a lot of women and men where the difference was a couple of years plus or minus. You know, oh, you married a gal that's 2 years older, you married a guy that's 4 years old, whatever. And then you'd run into somebody like Hugh Hefner who was 95 and his wife is 22. That's weird, okay? And so what does that do? It takes this ginormous data point and we take their differences. Or similarly, some old lady's got 50, 58, some old lady my age, 53 or something or whatever, who knows. And then she has a 25-year-old boyfriend or something on the Joan Collins deal or something back in the day. Well, that's weird or whatever. But okay, if that were the case, when you take those differences, you say you do men versus women, sometimes you're going to have a huge positive difference. Sometimes you're going to have a huge negative difference, but the spread is going to get bigger regardless. And so no matter what happens, we always add variances. And so that's the point of question one, is going through and talking about, well, question one and question two are going through and talking about, let's go through and verify what we did before. Also, it's talking about what happens when you multiply this whole column of data by 5. Well, I don't know. What would happen to that? Well, it would be 5 times the average for that column, obviously, which is exactly what was supposed to happen. The expected value of A times X is A times the expected value of X. But what would happen to their variances? Well, that would be a great deal different, and you'd want to go back and talk about that. So that is the point of questions specifically questions 2 and 3. Okay, is going through and just chasing those down with some actual numbers. Okay. If you have a hard time getting your Excel to do the add-on for you, Google Sheets used to have this cool add-on, but it doesn't work anymore. It's really getting on my nerves. So I guess if one or two of you like, all I have is a Mac and it doesn't work, if you send me this data like this, where you have the numbers you want to simulate and their probabilities, and they have to add up to 1, and this is for your X's, and then do another set for your Y's. If you send those to me, I will simulate your data and send it back to you, because that's neither here nor there. This is simply just a matter of getting data. And so if that's troubling for you, let me know and we'll work around that. It's the actual doing the cool things that I find I think it's going to be helpful to you. Again, you can do this. Here's 5x, let's say, equals 5 times this guy, and just paste it down. And so then what's the expected value of this column, 5x? Well, it's 5 times the expected value of this column. And you're going to see those things. That's kind of the point of doing this project in my mind. Okay? That help? Anybody still with me?
Yeah, I'm here with you.
That work for you?
Yeah. Do you think you could remind me when we're going to have office hours for this next week?
What's tomorrow? Thursday? I'll try to do office hours tomorrow if you want some help. And
Okay.
then we'll shoot for Tuesday next week as well. I had a staff meeting this week at Tuesday at noon because we didn't have Monday school, so that's why I didn't get that done. Let's shoot for tomorrow. How about tomorrow 7 work? I'll just do that. I'll be online tomorrow at 7 o'clock at night, and then
Okay, 7 p.m. You got it.
I'll email everyone as a reminder too. Okay.
Yeah, Jay, I asked some questions in chat.
Oh, sorry. Let's go find them. Where'd they go? Shoot, where's the dumb chat at? There it
Are
is.
you going to talk about the final project next week as well?
The what? The final project?
Yeah.
Well, it's not so much the Excel functionality. It's what I would like you to do is to understand that the expected value of A times X is A times the expected value of X. And I want you to see that based on numbers, okay? And I want you to see what happens when you take a column of X's and a column of Y's, and let's say you add them together. What does that do to the expected value? And what happens when you subtract them to the expected value? And what happens when you add or subtract based on what happens to their standard deviations or the variances? That's what I want you to go back and look at, okay? And so I can show them to you till you're blue in the face, and some people are good at picking up on that just from being told. But for me, like, standard deviations never made sense to me why you add variances even when you're subtracting. It didn't make sense until I looked at a column of data here and a column of data here. And when I add them, I see that I could, for instance, if you added 2 people's ages, if you add 2 people that are 26 years of age, you get 52. And that's great. You get a lot of first-time people getting married in their 20s, and so you get a lot of data that would be in their 50s and 60s or whatever, and some in the 40s, I guess, too. And then you get, Hugh Hefner, who's 92 or whatever, and his 22-year-old bride, and then you also get a 111-year-old one over there. And you get people who get married when they're 17, you get this 31 that's kind of a weirdo down here. So what happens, whether you add or subtract, the standard deviation of the variance always gets bigger. And so the purpose of this is just to help you visualize that better, help sell it in your mind. Okay, that's kind of why I like to do it.
Okay, cool. That makes sense. And then don't forget to post the last week's video.
Do it right now. Thanks.
Thank you.
All righty, everyone. Have a nice week.